Hi guys, so today we're going to take a look at question 8 from paper 2 of the 2015 exam. Okay, so in basketball, players often have to take free throws. When Michael takes his first free throw in any game, the probability that he is successful is 0.7. Okay, so his first free throw has probability of success 0.7. For all subsequent free throws in the game, the probability that he is successful is 0.8 if he has been successful on the previous throw, and 0.6 if he has been unsuccessful on the previous throw. Alright, so that kind of makes sense. The chance he's going to score is affected by how his last shot went. So if he just scored, he's more confident, so he's more likely to score. Alright, so if we get this down in maths, the probability of success on first equals 0.7. And then probability of success given he failed previously equals 0.6, and the probability of success given he just succeeded previously is 0.8. And this will form the kind of groundwork, these probabilities will form the groundwork of how we're going to approach this question. Now onto part A. Find the probability that Michael is successful with all three of his first three free throws. Alright, so we want to break down what has to happen for this to be the case. Well, I know this might sound silly, but he has to score the first, and then he has to score the second, and then he has to score the third. And you might say, well, really? But this makes it easier to kind of break it down into what events need to occur. Okay, so, well, what's the probability that he score the first? Well, we've just written that down. The probability of the success on first, success being a score, is just 0.7. And now, then he has to score the second. So we're looking at the probability that he score second given scored first. Alright, well, that's the probability that he succeeds given that he just succeeded. So that's just 0.8. And then finally, probability that he scores third given score second. And again, probability that he succeeds given he just succeeded, 0.8. And when we have these three probabilities in a row, we just get that they multiply. So the probability of all three happening, you just multiply the probabilities. That's 0.7 by 0.8 by 0.8 is 0.448. 0.448. Now on to part B. Find the probability that Michael is unsuccessful with his first two free throws and successful with the third. Alright, so again, what has to happen here? Well, he has to miss the first, miss the second, and then score third. Okay. So this is just probability of miss the first, which is just, well, he either scores or he misses. And the probability that he scores is 0.7. So the probability that he misses is 1 minus 0.7 is 0.3. Okay? So now he has to miss a second. So probability miss second given miss the first. And so the probability that he scores given that he misses the first is 0.6. So the probability that he misses given the first is 0.4, 1 minus 0.6. And then finally, probability that he scores the third given that he missed the second, score third given miss second. Oops. So the probability that he scores third, succeeds given that he misses is 0.6. And again, we just multiply these together, 0.3 by 0.4 by 0.6 equals 0.072. 0.072. Let's just highlight these answers. Now on to part C. List all the ways Michael could be successful with his third free throw, and hence find the probability that Michael is successful with his third free throw. All right, so in what ways could he be successful with his third free throw? Okay, so let's try and write them down. Well, he could score first. He could score all three. Score first, score second, and score third. Okay, that's the first thing we worked with. He could miss the first two. So he could miss the first, miss the second, and then score. He could score first, then miss, and then score again. Or he could miss first, score second, and then score his third. So these are all the ways that he can score on his third shot, okay? And hence find the probability that Michael is successful with his third free throw. Okay, well, probability of scores first free throw. Probability he scores third equals the ways he can score third by probability that happens. So we can just find the probability of, let's call this outcome A, this one B, this one C, this one D, and all of these will lead to him scoring third, and they're the only ways he scores third. So we can just calculate the probability of A. So probability of A plus the probability of B plus the probability of C plus the probability of D will be the probability he scores third. Okay, so let's just make some space. Okay, so, well, what's the probability of A? The probability that he scores all three, well, we already figured that out. It's 0.448. 0.448. The Probability that he misses the first two and then scores, well, we also figured out that one. It's 0.072. Okay. So he scores the first, which has probability 0.7. And then he misses his second shot, given that he just scored his first. So that's 1 minus 0.8. So by 0.2. And then he scores his third. So 0.6, the probability that he scores, given that he just missed. So this equals 0.7 by 0.6 by 0.2, 0.084. Okay, and now the probability of t, so let's just plus 0.084. The probability that he misses the first, so that would be 0.3, scores the second, so the probability that he scores given that he just misses, which is 0.6, and then scores the third, probability that he scores given that he just scored, which is 0.8. So this is just 0.3 by 0.6 by 0.8 is 0.144. So 0.144. So if we sum those up, we get 0.748. So that is the probability that he scores the third shot. Okay, so on to part D. Let Pn be the probability that Michael is successful with his nth free throw in the game, and hence 1 minus Pn is the probability that he's unsuccessful. Show that Pn plus 1 is 0.6 plus 0.2 Pn. So Pn plus 1 would be the probability that he's successful with the n plus 1th free throw. Alright, so we've just calculated P3. So how would this happen? Okay, so how would he score his n plus first? Well, so the probability of n plus 1. Well, he could score after just missing, score after missing, or he could score after scoring. And that's the only two ways it can happen. Either he just missed or he just scored. Okay? So this would be probability of n plus 1. Well, is 0.6 times, well, he has to have missed the nth shot, and the probability that he misses the nth shot is 1 minus Pn. Okay, or he could score after scoring, so that would be the score. So he's just scored, so his probability is 0.8 by the probability that he scored the nth shot, which is just Pn. So these are the ways he can score the n plus 1th shot. So we just sum these up to get the probability, Pn plus 1. So 0.6 by 1, so we get 0.6 minus 0.6 Pn, and then plus 0.8 Pn. So we just get 0.6 plus 0.2, 0.8 minus 0.6 Pn equals Pn plus 1. So we have shown that Pn plus 1 equals 0.6 plus 0.2 Pn. Okay, so on to part 2 of part D. Let's assume that P is Michael's success rate in the long run. Okay, for large values of n, we're saying that Pn plus 1 is approximately equal to Pn is approximately equal to p. So it's saying that Pn kind of levels out at some point. So using the result from part 1 above or otherwise, show that P equals 0.75. Okay, so we're going to use our result from part 1 and show that it's equal. Well, we know that Pn plus 1 is approximately equal to Pn. Okay, so if we have this formula, Pn plus 1 equals, our result from above, 0.6 plus 0.2 Pn. And if we know that Pn plus 1 is approximately equal to Pn, which is approximately equal to P, well, we can just sub in P wherever we see Pn plus 1 or Pn. So P equals 0.6 plus 0.2 by P. And now we just need to solve for P. So if we bring over the 0.2, we'll get P minus 0.2P equals 0.6. So P by 0.8 equals 0.6. And so P equals 0.6 over 0.8, which just equals 3/4 or 0.75. So very simple. It's just important to notice that we're going to be using the result above. So if you know that we're going to be using the result above, you might as well just immediately write down the result above. And we know that we're looking for P such that Pn and Pn plus 1 are the same. Now on to part E. For all positive integers n, we're going to let an equal P minus Pn, where P equals 0.75, and we're going to use the ratio an plus 1 over an to show that an is a geometric sequence with common ratio 1/5. Okay, so it's giving us, so an equals P minus Pn, that's our expression, and P equals 0.75. And we're going to use the ratio an plus 1 over an to show that the an's are a geometric sequence with common ratio 1/5. All right, well, what's a geometric sequence? Geometric sequence, so that would be one where sequence with a common ratio. Common ratio. So for example, it could be something like 1, a half, a quarter, an eighth, 1/16, and so on and so forth. So that would be a geometric sequence because there's a common ratio between terms. So the 1/4 to 1/8 is multiplying by a half. 1/8 to 1/16 is multiplying by a half. There's a common ratio of a half there. So this sequence would have common ratio 1/2. And you can find the common ratio by dividing one term by the term before it. So, for example, 1/4 over 1/2 gives you a half, and we know that that's the common ratio. Okay, so if we get rid of this example, make some space. Okay, so now we want to show that an plus 1 over an, so if this is a constant, then we know that the an's are a geometric sequence. So if there's a common ratio of an plus 1 over an, then the an's are geometric. All right, so what is an plus 1? Well, an plus 1 equals P minus Pn plus 1 all over P minus Pn. Okay, well, what is Pn plus 1? Well, we already have a expression for this. So it's P minus 0.6 plus 0.2 pn, 0.6 plus 0.2 pn, all over p minus pn. Okay, let's just make some space. Okay, so, well, we know that p is 0.75, so p equals 0.75. So we're just going to plug that in. So we get 0.75 minus 0.6 minus 0.2 pn all over 0.75 minus pn. Right, so the top gives us 0.15 minus 0.2 pn all over 0.75 minus pn. And what you'll notice is, because 0.15 is 1/5 of 0.75 and 0.2 is 1/5 of 1, this whole thing just becomes 1 over 5. And so if you notice that it doesn't have anything to do with n, so it doesn't matter what n is, this ratio is 1/5. So there's a common ratio of 1/5. So the sequence an is geometric. And they asked us to show that it's a sequence with common ratio 1/5, and that's exactly what we've done. Now on to part 2 of E. Find the smallest value of n for which p minus pn is less than 0.00001. Okay, well, so it's straight away it's said p minus pn. Well, we know that p minus pn, we've been calling that an. Okay, so what we're looking for is the smallest n such that an is less than 0.00001. Okay, well, let's try and find out what an is. Let's see if we can make a formula for it. So let's first find out what a1 is. Well, a1 would be p minus p1, and p is 0.75, and p1 is the probability that he scores the first shot, which is 0.7. So this is just 0.05. So a1 is 0.05. Okay, and because this is geometric, a2 equals 0.05 by 1/5. Okay, and a3 equals 0.05 by 1/5, so a2 by 1/5 again, or equivalently 0.05 by 1/5 squared. a4 is a3 by 1/5, so 0.05 by 1/5 squared, which is a3, by 1/5, so by 1/5 cubed. And so you very quickly notice a pattern here and a nice formula popping up where an is just 0.05 by 1/5 to the n minus 1. So for a4, it's 4 minus 1, so 1/5 cubed. For a3, it's 3 minus 1, so 1/5 squared. And this gives us a nice formula. So we're looking for an. Let's first let it equal to 0.00001, and then just go to the next n. So we're going to let that equal, so our formula for an And now we're going to try and solve for n. So if we divide both sides by 0.05, we get 1 over 5,000 equals 1/5 to the n minus 1. Okay. And now how do we solve something like this? Well, we're looking for 1/5 to the watt equals n minus 1. And this is basically the whole idea behind logs. Something to the watt equals something. So this would just be log of 1/5. So 1/5 to the watt equals 1 over 5,000. So if we just put that in, log the 1/5 equals 1 over 5,000. And that's 5.29. So 5.29 equals n minus 1. So n equals 6.29. But 6.29 isn't a whole number. So for n equals 6, it's bigger than this because it's constantly getting smaller. And for n equals 7, it's smaller than 0.00001. So n equals 7 is the smallest n that an is less than the number we're looking for. So for part F, we arrive at a game in which Michael is playing. We know that he's already taken many free throws. So he's already taken many free throws, but we do not know what pattern of success he's had. Okay, so we don't know if he's just scored or if he's just missed. Now, based on this knowledge, what is your estimate of the probability that Michael will be successful in his next free throw in the game? Okay, so we don't know what's just happened. If we did, then we could just straight away say what the probability that he'll score his next shot is. But we're looking for the probability that he scored his nth shot, okay? Because we don't know what's come before. We're just saying, what's the probability he scores his nth shot? And we know that n is large. He's already taken many free throws, okay? And we know that for n large, Pn is approximately P. Well, we actually see that it gets there very quickly. You know, after only 7 free throws, then the difference is already less than 0.00001. So it gets small very quickly. Okay, so we can just say that Pn is equal to 0.75. So we're guessing what is the probability he scores the next shot, so some nth shot, whatever n is. And we know that this is around 0.75, so our guess is that the probability he scores the next shot is 0.75. Now on to the last part of this question. Why would it not be appropriate to consider Michael's subsequent free throws in the game as a sequence of Bernoulli trials? Okay, well, first of all, we see the word Bernoulli trials. So what is a Bernoulli trial? A Bernoulli trial is a sequence of independent events that can either be a success or fail. And they have the same probability. So for example, an example of a Bernoulli trial would be if I am flipping a coin. So this result of the fifth flip has nothing to do with the result of the previous flips. So they're independent. And I can either get a heads or a tails. So there's two possible outcomes. So in this case, so let's see, does this situation fit this criteria? So success or fail? Yes. He can either score or he misses. Sequence of independent events. No, the events are not independent. So if he scores the fifth, that actually affects whether or not he'll score the sixth, because he'll be more confident, so it'll be a higher probability, and if he misses, he'll be less confident and it'll be a lower probability. No. So it cannot be considered a Bernoulli trial, considered a sequence of Bernoulli trials. Now on to the last question. Why would it not be appropriate to consider Michael's subsequent free throws in the game as a sequence of Bernoulli trials? So, well, what the hell is a Bernoulli trial? Well, a Bernoulli trial, or a sequence of Bernoulli trials, is a sequence of independent repeated events that have only two outcomes. Success or fail. Okay, so let's see, does Michael's subsequent free throws, does that fit this criteria? Well, it's repeated events. Repeated events, yeah, it's the same thing. He's taking a free throw. Repeated events, yes. Success or fail, are there only two outcomes? Yes. He can either score or he misses. But are they independent? Independent? No. The events are not independent. So how he does on the sixth throw, if he scores or misses, that does have an effect on how he does on the seventh throw. It's like, so a sequence of Bernoulli trials would be flipping coins. It's the same thing, you're just flipping a coin. You can be either heads or tails. And whether or not I get a head on the fifth go says nothing about what I'm going to get on the sixth go. There's events are totally independent. Whereas in this case, our repeated events are not independent. So it cannot be considered as a sequence of Bernoulli trials. As a sequence of Bernoulli trials. Because the events are not independent. Because the free throws are not independent. And it's just simple as that. But it's important to know the definition of a Bernoulli trial, to know what that is. If you don't know what a Bernoulli trial is, it's impossible to answer this question. And then we've got to get the probability that C occurs